Okay, so it looks like it's working. Okay, so now I'm going to share my screen. And I'll go to this view here. Okay, so I'm going to throw a positive charge in here. Okay, and you've got the, dipoles aligning. So you've got the positive charge and you got the negative charge, and the, positive charges, point away from. Now, I'm not a big fan of this, of using arrows. What I would prefer to see, it's just they're sort of making the out arrow seem kind of more important than the inner, so I would like to see like two arrows, a blue arrow and a red arrow, and the red arrow points away from the red arrow and the blue arrow points towards the red arrow. Because
is this again a JavaScript simulation? Is it similar? Like, could you actually color the arrows? But
well, I might make my own. I might make my own simulation for this. Like once because this is actually, this wouldn't be that hard to do. Probably something like this with the P.
Yeah,
like,
right.
When we do the wave, like how you did the two waves. You did two waves. You show the interference pattern. You show how much that looks like a. So sometime I want to do something like that. So in my opinion, the ether looks like the arrows. So every point in space has an arrow. It's a tiny vortex, like in the Bose-Einstein condensate. I'm going to say BEC because I can't say that long word.
Yeah.
In the BEC, like John showed in his paper, where you have these tiny little solitons forming in the medium, in the BEC medium, which is in a hexagonal pattern. Each of those little dots would align. If you threw a charge in there, it would align like it does in a electric field. Okay. So what's the difference between an electric field and a magnetic field? I know there's the first two Maxwell equations, right? The first one is the the equation for charges, and the second one is the equation for the magnetic field. And for charges, you've got the divergence of the field is non-zero. Okay. And what that means, can you see my arrow moving? Or is my mouse moving? Sorry.
The mouse is moving, yeah.
You can see the mouse moving in my, okay. I'm not sure because it's very tiny. Okay. So you can see that, as I move this charge around, that the arrows are pointing. So for the positive charge, all of the arrows are pointing away, so they're diverging. And for the negative charge, all of the arrows are pointing towards it, and so they're converging. Okay, so that's the divergence is non-zero, because you have divergence / convergence, because it's not just about divergence, but divergence and convergence is non-zero. But so what happens is, I'm going to show you what happens when, in this simulation, it's really crude, okay? It's really coarse, obviously. The magnetic moments of the ether would be so, we can't see them because we are them. We are them, basically. Okay, so this is the divergence of the field is still non-zero because you have arrows moving away and arrows moving towards. But when you take the negative charge and move it really close to, and have it, you see that arrow turning?
Yeah.
Right. The blue arrow is now turning towards the one. Now we have, in this field here, we have divergence of B is not equal 0. Here we have a magnetic field, right? Okay. So the only difference in my mind between a magnetic field and electric field and a magnetic field is the electric field are unbound charges. That's the field you get when the charges are unbound to each other. And the magnetic field is what you get when charges are bound. Now they're touching. When they're bound to each other in a object, in an atom, then you get this condition where the divergence of B is not equal to 0. This is technically a magnetic field. So that's kind of how I see the ether in both. So there's really no difference. There's not two ethers, one for electric field and one for magnetic field. There's one ether that behaves the same way for both an electric field and
yeah. I definitely agree there should only be one field. So
Yeah.
the question is, in your model, the $1 million question is, what is that charge itself? Is it just the arrows? So is the plus and minus that you put there just a visual aid? So there's only the arrows.
Yes.
There's no,
Yeah.
or is there something extra?
The arrow would be the soliton wave that John's talking about, but at the Planck scale.
Oh, okay, I
So
see.
at the Planck scale. So I don't know if he has that, because his math is a little different at the Planck scale, because he talks about Planck length as being the wave amplitude, and for me, the Planck length is the size of the soliton, the quantum soliton, which makes up the medium for the propagation of light. So which is analogous to or self-similar to the soliton for the electron, the soliton for the proton.
So I see. Okay. So what do you imagine this charge to look like, though, as a wave function? Do you think it's just a miniature version of the spin, or spin 1/2? The spin 1/2 is like the large wave, and this is like tiny. How do you imagine that?
So the way it works, the smaller the wave, so we can maybe get back to the wave stuff. I think you kind of get this, right? So I wonder if I have something I can show you. I want to talk about that at some point. I don't know if I have my slide for my model, but I use the own particle. I use the yin yang, right? I use the yin yang for my model.
Which is funny, because the spin 1/2 simulation looks like yin yang.
It does.
I thought it does, right?
I was really kind of blown away by that when I first saw John do it. Because that's the first time I actually saw that kind of a wave. I was like, oh, that looks like yin yang. That looks like my model, and so that's why I started studying him, because of it looked like the yin yang.
Yeah. And
so let's see. I'm sorry, I'm not I thought I was prepared, but I'm not that prepared. Okay, so there's my yin yang model. Okay, so in my yin yang model, I think it's a really nice schematic, actually, for this particular for the soliton that John's talking about, that you guys are talking about. So this is a hill, and this is a valley. So this is a schematic. So dark to light is a hill, and light to dark is a valley. So this would be a nice, like, how else do you represent on a static 2D image? How do you
perfect. No, it's really good. Yeah.
So you get
this could be simple spin 1/2, right?
Yeah, exactly. This is spin 1/2. This is spin 1/2. So you get the idea of spin. So this would be the rotation part of the algorithm. And then you get the twist, which creates the sine wave kind of thing. So creates the hill and the valley. And the steeper this is, and this John talks about the steepness of this, you get the different sort of patterns, right? So this would be maybe where you go 180 degrees might look like this, right? Where the twist is 180 degrees might look like this. So this would sort of give you the idea of the twist. So the twist isn't represented in this model, but you can't get the hill and the valley without the twist, right? You can't get the hill and the valley without the twist. So you get the spinning, you get the twist in this schematic. So in my model, this is an electron, this is a proton, and this is I call it a known particle. This is the one at the quantum scale, which would have the Planck mass. The outer perimeter would be Planck length. So I'm dealing primarily in cyclic phenomenon. So I don't do my stuff in radians. I do everything in terms of cycle.
Oh,
so
yeah.
I'm very kind of anal about this, so it pisses people off, like John. Anyways, I won't say anything, but anyways, it kind of annoys people, because I'm very, very, very picky about this. And I do, so when you do,
either way, it's fine with me. I have to. The important thing is to get the meaning across, right?
Exactly. And I think being a computer scientist kind of makes me this way, because I'm very picky about how I write my programs. And so what I'm doing is I'm writing a schematic, or not schematic, but like a template or a specification is the word I'm looking for. So I'm building a specification, and in my specification, all the parameters are in terms of a cycle.
Oh, okay.
When I write Planck's energy equation, I write E equals HF. I don't write E equals H. I don't use H bar. And when I do my Planck calculation, natural unit calculation, I do them using H and not H bar. Everyone else in the world uses H bar for that.
It's just a factor, right? Yeah, people will understand. Yeah.
I'm kind of like a jerk. No, I'm an asshole. Sorry. I annoy people because I'm very picky about this, and Dawn and I argued about this forever. And so, yeah, I didn't mean to say that, but anyways,
One question I have. So when we model the electron, like the spin 1/2 wave and all that, it's huge, right? Compared to this size, compared to Planck size, it's many orders of magnitude larger, right? So this is tiny, right? This will be gigantic wave. This is tiny. So are you saying there are these vortices at multiple levels? So we have the very gigantic spin 1/2 wave at the electron scale, which would be can't fit even on the screen, right? And then you have at the Planck scale, you have again, these are like tiny little waves.
They're tiny, but they're exactly the same. So let's just say that in the fractal paradigm, they have the property of self-similarity. And so you've got the big wave, the large scale wave. I don't want to call it big, the large scale. So in the fractal paradigm, we talk about scales, right? So you have the large scale, which is the electron, and then you have the medium scale, which is the proton. Protons are spin 1/2 too. And I think
they are, yes.
Okay. And then my quantum particle is also a spin 1/2. Okay. So, this is sort of the way I'm looking at it. Instead of saying that, electron is one thing, proton is another thing, and quantum is another thing, I'm saying they're all the same thing.
Yeah. So in the wave model of matter from Robert Close, right? Everything is waves basically. So the electron is a wave shape, I guess. Proton is a wave shape, the neutron, the neutrinos, they're all just waves of this.
And you can stack the waves to get different, you can stack the waves to get different patterns and that sort of thing. So, so let's talk about this. I'm going to show you, let's talk about the wave function, because what I realized was, now I don't know if you're familiar with the isopotential.
I've implemented this in Java and in
so there's two magnetic fields. Magnetic field with the arrows that's the one they primarily show, and then there's the potential, the isopotentials. And what I discovered was the isopotential pattern matches exactly with the wave function probability.
Nice. Okay.
Right. So this is software that was written by Michael Snyder that I did for the isopotential. So I used his software, and I would, you place magnets in different patterns, and you get these different patterns. So this isopotential is just when you look at just the one pole, right? And it looks like the 1s orbital of the atom. And then when you have a dipole pattern, it looks like the, 2p whatever orbital. So the patterns match exactly, so this is the first scale, the first iteration. And then when you get to the next iteration, you've got the, similar kind of a pattern where we have the, that one magnet. And when you put the magnets in the same configuration that they're showing in these orbital drawings, you get the same isopotential.
Really? Wow, so, that's amazing. Actually, that's amazing.
So this is something that I never saw before. So when I realized this, when I started building these patterns, I'm like, why do they look familiar? And then I realized, and then I saw these pictures. I'm like, those look like the isopotentials. So I kind of put 2 and 2 together. So here you can see there's, this is sort of how they configure. So I think this is really interesting. So this is another
definitely interesting.
In my opinion, atoms are really just magnets. When you get so this is where you get, when you have the positive and negative charge are bound to a object, then they're a magnet. When they're not bound to an object, then they're a charge. So when the positive and negative charges are separate, like I said when I was showing the other visualization, when they're apart, you get the divergence of the field is not 0. And when they're bound, then you get the divergence of the field is 0. So that's the only difference between charge and magnetism.
Okay, cool.
So this is the atom, and this is the magnet. Okay, so I could take that to the next scale, which is the large scale. Okay, so here we go. So this is the picture of a black hole.
Black hole, yeah. Mm-hmm.
Okay, and on the right is the picture of a ferrocell. Now, I don't know if you know what a ferrocell is, but basically,
heard about it, but I haven't thought much about it. So yeah.
Okay, so basically, you take a medium, which is dipole, which are magnetite, I think they use. So magnetizable medium, not a magnet, but a magnetizable, polarizable medium. So I'm saying the medium for the propagation of light is a polarizable medium.
Okay, yeah.
So when there's no charges, it does nothing, and when there are charges, right? So in the ferrocell, what happens is you've got these nanoparticles, which is the ferrofluid. So you take the ferrofluid and you mix it with some a medium of some sort, just something to make it slip between the two pieces. And then you take 2 optically flat pieces of glass, and you put the fluid on one layer, then you put the glass on, and it spreads out nicely. So you mix the ferrofluid with baby oil. Actually, I use baby oil for some of it, so it spreads nicely. And then you get this nice thin layer between the 2 pieces of glass. Then you put a set of lights around it. So let's see, I think you can see the lights here. Okay. Yeah. So then you put a bunch of lights around it, pointing, towards the glass, and it illuminates the lights reflect off the nanoparticles. So when you put a magnet in place, the nanoparticles align like they would normally, just like iron. They're just tiny iron filings. They align with the magnet. And then when you shine light on it, it creates this pattern, which looks an awful lot like the pattern that the black hole makes.
Interesting. Yeah. Wow.
So that's another connection. In my mind, a black hole is just a giant magnet. And all we're talking about here are how tiny magnets behave near large magnets. So everything, all of the charges, the animation I showed you, or the visualization with the charges and everything, that's a small dipole moment in the vicinity of a very large dipole moment. Okay, so that gets us to, I don't know if we're getting off track here, but I'm on a line of thinking here. So let's finish this. Because it is related to the medium, which is really what we're talking about here. Okay, so the Stern-Gerlach experiment, where they discovered up electrons and down electrons, this experiment, the interpretation of this experiment kind of bothers me, because they're showing these arrows pointing one direction, right? And they're showing them randomly aligned, and they're showing them going through here, and then landing. They expected them to land, here, and here, but really some go up.
Yeah, that always bothered me too. That's just crazy.
But if you think of this as a small dipole moment in the vicinity of a large dipole moment, then what I can do is I can put the isopotential diagram in here.
And then you would just align, right? I mean, it's kind of
exactly. So then you realize, oh, wait a minute, this magnet, so there's a silver atom, there's a tiny electron, whatever. This is electron is going to align with the magnetic field. Okay, so it's not going to be, this is going to point up, and this is going to point down. And that doesn't mean everything's going to, that's why arrows are a problem. That doesn't mean that if this is pointing up, that this is going to point up. Okay, what's going to happen is if this is north and this is south, if the top one's north and the bottom one's south, so the south is going to point up and the north is going to point down. This is going to align with this magnet. And if it's just a tiny bit above the center line of the isopotential field, it's going to go up. And if it's just
that makes sense, right?
Low, it's going to go down. I can do this with if I take a small spherical magnet and have a big spherical magnet, or any magnet, doesn't matter, and I put the small magnet near the middle of the big magnet, it's going to be kind of unstable. Like I can actually place it there and let go and it'll stay. But if I touch it, it's either going to go up or it's going to go down, but it's always going to align the same way. It's never going to point up or down. It's always going to point in this. It's going to align the south with the north and the north with the south. It's going to align. And if it's just a tiny bit above the middle line, it's going to go up. And if it's just a tiny bit below, right, it's going to go down. It's going to follow these isopotential lines. And I've done some experiments that I show on my YouTube where the magnets, the small magnets, if there's a tiny bit of friction, which there would be because there's air and stuff going on, it's not done in a vacuum. It's going to follow the isopotential line, right? It follows it. So I've done some experiments where I prove that it does follow this. When I take on a table, when I take two magnets, so I have one magnet here north, another magnet, and I separate them. And then, or actually, if I take just one magnet and the north is here and I place a magnet back here and then let go, it actually goes like this and then flies to the magnet, right? It actually goes like this. And then, so it doesn't just fly to the magnet. It actually, because there's a little friction on the paper, it actually, the path of least resistance, it can't go this way because it's aligned with the magnet. So it can't roll that way. So the spherical magnet can actually roll this way and then it flies to the magnet, right? Cool. So I think this experiment is misunderstood. I think they did another experiment where they're saying, oh, there's up electrons and down electrons, which is weird. Okay.
Yeah, that is weird.
So they did an experiment where they said, okay, there's up electrons and down electrons. So then they put another experiment here where they took all the up electrons and put them through another Stern-Gerlach experiment and they split again. And they're like, oh, why are they splitting again? Well, this is like there aren't.
Exactly. If it's just a wave function, it's not either. I mean, it makes no sense to call it up or down, right? It's just going to align.
Like saying it's like saying there are up magnets and down magnets.
Well, the thing is, you have the particle model, right? You have to have these fixed things, these fixed properties. When it's a wave model, it's all different, right? It resolves all these paradoxes in my mind. So
So those do generate paradoxes. And so without a medium, there's a lot of paradoxes.
Yeah.
With a medium, all the paradoxes go away.
Yeah, exactly. Yeah.
And then you can deal with everything in the same way if you think of everything as a small magnet in the vicinity of a large magnet. So that's the atom. So the electron, or a weak magnet in the vicinity of a strong magnet. I guess like a small magnet, weaker, right? So instead of thinking in terms of size, think, weak magnet in the vicinity of a strong magnet. And so for the black hole case, the ether is the weak magnet. When in the black hole is a very, very strong magnet, like the strongest magnet, we know there's magnetic fields around black holes. There's no black hole without a magnetic field around it, right?
Yeah. I mean, you see the pictures, right?
And so, so that's sort of my holistic approach, thinking like a fractal. Okay, I see. Okay. The universe makes the same thing over and over, does the same thing over and over and over again, but at different scales. Right. Cool. So the atom's a magnet, the electron's a magnet, the atom's a magnet, a magnet's a magnet. Small magnets, large magnets, and the black hole is also a magnet. So that brings us to the whole cosmological scale.
Cool. You know what? I'll bring it up with Robert Close and ask him what he thinks about it. The dipolar medium, because we've only talked about the medium in general, like the properties it has to have in terms of speed of light and elasticity and all these things, but not the actual constituents, right? Do we know anything about it? Is there any property we could derive? Is there any experiment we could do? So I'll ask him about it. See,
it's funny because all the experiments we do could also be interpreted. If we had a medium, could be interpreted. So it's is there an experiment we can do that can tell the difference? No, because you can interpret it, if there's no medium, you interpret it this way. And if there is a medium, you interpret it this way.
Yeah. There might be. So there's one experiment that might be possible, that if the medium is not continuous, if it's continuous, I think we have no chance, but we don't know for sure, right? But if there is a smallest, like a Planck scale, if there really is a smallest, like the end of the fractal, then it's possible that when you have light waves that are extremely short frequency, like at the order of the Planck length, that speed of light would change slightly at that level. So if we could observe like gamma ray bursts from that are highly redshifted, it's possible we might be in the future be able to detect if there's a small difference in speed of light. But that's the only thing I could imagine that might.
Yeah, that's very tricky, because like gamma rays are just in the order of the dimensions of, say, the proton. So
they're way too large. We need proton, many orders of magnitude more smaller, right? That's the thing.
Exactly. So X-rays have the frequency similar to the electron Compton frequency. And protons have gamma rays have the frequency similar to the proton Compton frequency. And I don't think we've been able to detect anything beyond gamma rays. So we can only atom. We as humans are made of atoms. All the devices are made of atoms. All the detectors are made of atoms. The only way we can detect light is with atoms. Atoms absorb, atoms
exactly, right? Yeah.
So and if the atoms are made of the medium, right, are composed of the medium, or the medium in motion, or the medium waving, then it's kind of like, how do you detect that? Because you can water detect water?
Can water wave? So could water waves, like aliens made out of water waves, construct devices made out of water waves that could detect the water particles? But that's the question. It's probably not possible, but who knows? I mean,
it's tricky. It's once you get can something made of a medium detect the medium?
But there are other ideas. If everything is really composed of waves, maybe we can construct new waves by combining waves, new wave shapes that wouldn't be possible if it was a particle world. Because waves you can combine, and then by having these interferences, you could create new kinds of waves. So that could be an approach. Something
and
that you can
did that. Nature already created all kinds of waves. These are wave functions, right? These are wave functions. The orbitals are really wave functions. Nature does kind of do that.
And the fact that you can actually collide, in quote, particles, and you get light out of it. That's just a transformation of a wave, right? Like you have one wave shape and you turn it into another wave shape. I mean, how do you explain this with particles, or the matter antimatter collision? If it's those particles, how do you explain that? That seems crazy, right? But if it's all waves, you just transform one shape of a wave with another one, like you combine it and you create new types of waves. It's kind of trivial almost, right?
Well, because it's just wave. The only thing waves can do is wave.
It's just different shapes or combinations of
and waves can interfere, and so here's the thing that kind of bothers me, because waves, when they talk about constructive and destructive interference, when waves are going in the same or opposite directions and they meet each other, they do all this constructive and destructive interference, and they come out the other side unchanged. So you're not destroying anything. It's not destructive. Like when they say destructive interference, you think, something's destroyed.
Well, I guess I mean like with a double slit experiment, right? When you have the wave overlapping, of their areas where a plus and a minus will give you a zero, right?
But so that's the only reason the waves don't come out the other side is because they hit the detector before they come out the other side, right? So they see the constructive and destructive interference, but left on their own, those waves would just go through each other and come out the other side, travel along their way, and nothing would change, right? Other than if the medium is not perfect, it's going to lose energy as it goes, and eventually will
that's another topic maybe for another time. But just briefly, if imagine if the light that's going through the mediums loses energy over billions of light years, what you get? You get a redshift.
Yes. I've always thought that. I've always thought that.
So, you know,
it makes sense.
I
Like,
don't,
so things that are red shifted aren't really far away necessarily, right? Yeah, well, it does.
I guess.
No, it does. Actually, no, you're right. It does make sense that things, you know, they would lose more energy over time, so they would be farther away because it would have had to go through the medium for longer.
Yes.
Redshifted things are farther away. Now, are you familiar with the work of Halton Arp?
Of course. Yeah. This is I have a whole blog post on all this stuff.
Okay. Oh, good.
See,
Yeah.
Okay, we get way off topic, but the problem is once you.
It's all interconnected. It's not off topic.
Yeah.
Right?
No, it's connected because see, once you have a theory, it has to match everything. It has to fit the special relativity, general relativity, the universe. Everything has to. All these pieces have to fit together.
Yeah.
And the problem is they don't like. I used to ask these naive questions on forums, like how, because there's different kinds of redshift that we know of. Like we know about gravitational redshift. Yeah. We know about, sure, if you would in theory expand space, you would be redshifted maybe, but also if the photon loses energy, you get redshift. And also if things move just away, just plain old Doppler effect, you also get a redshift, right?
Yeah.
So exactly. I would ask this naive question, how do we know what percentage is space expansion versus gravitational redshift versus Doppler effect? You get no answer. So that's what bothered me initially, because the assumption is it's all space expansion, period. There's no discussion. If you ask the question, you're like a heretic.
This space expansion and that.
Like, what?
No.
How do we know? We just assume? How can we just assume and build a whole theory on top of that, right?
Well, yeah. I mean, most theories start with assumptions, so there's nothing wrong with
assuming. That's fine. Yeah.
These questions. We need to be able to ask these questions. And so what Halton Arp found in another kind of redshift, he calls it intrinsic redshift.
Yeah, with the quasars right on front of the galaxy.
Yeah.
So another kind of redshift, maybe it's not all just one kind. Whenever a photon loses energy, it will be redshifted no matter how it lost its energy, you know. Yeah. So there may be many mechanisms of photons losing energy, you know.
Yeah, exactly. And so his theory was that when the quasars are ejected from the galaxies. Mm-hmm. These quasars are ejected from the galaxy. So it's ejected from the galaxy, and as it gets further and further away from the galaxy, it becomes less and less redshifted. It becomes more blue shifted. And then when it's far away from the galaxy, that's when it becomes a mini, what do you call that? A dwarf galaxy.
Yeah. Okay. So, yeah, I've read about that. Yeah.
Born. Mm-hmm. I like that.
And he found many pairs, right? He found many pairs that are statistically, you could say, oh, it's coincidence, but there's so many examples that, one or two, of course it could be coincidence, but there's so many, like,
he was the master of quasars, so.
I know, I have the book in my room, so no, this I read it because it has to fit all together, you know. I'm like, and the other thing is, when you imagine, I have this grid in my screen, right? If photons are waves in that grid, right? Yeah. When you the whole grid, of course, then you would stretch the photon. So that part makes sense, right? But that means also when you stretch the grid, you would also stretch electrons, and you would stretch protons. You would stretch all of matter. Yeah. And now the thing is, when you stretch everything, then again, there's no expansion, because we measure everything with electrons. If the electrons is twice the size and the photon is twice the size, well, there's no we wouldn't notice the expansion. You know what I mean?
Exactly. We wouldn't measure the redshift. Now, here's another.
He wouldn't make it different. So how do you explain it? So basically, what they're saying is, well, only photons are stretched. So somehow photons are tied to that space for some weird reason. Even though there's no absolute space, right? They're saying there's no absolute space, yet photons are stretched when you expand space, but it doesn't affect electrons. That just doesn't. No. I mean, either there is no space, fine, but then there's nothing to stretch and nothing will expand. So, or everything is attached to space, and then everything stretches. So,
So the everything stretches. There is one way of the everything stretches idea, and it has to do with the fractal paradigm again. My friend Blair McDonald wrote a paper on this. He did a few experiments. He wrote some code to do this, and what he did was, so he imagined that the universe is a fractal, right? And that fractal, each time you iterate the fractal becomes more and more complex. So with each iteration, you get more. You
like
get
galaxy clusters and clusters of clusters and so on and so on and so on.
So yeah, exactly. So the first iteration is sort of this coarse thing. Next iteration, you get smaller things. The next iteration, you get smaller things. That's the Mandelbrot too. As you zoom into the Mandelbrot set, you're looking at smaller and smaller scales.
Yeah.
Okay. So what he did was he imagined that, what if I was like sitting on the fractal and the boundary of the fractal, at the edge of the fractal, or on the fractal, and then could look back in time. If I could look backwards and see what the universe looked like when it was less iterated, it's going to look more redshifted.
Oh, I see what you mean.
Right? But the laws of physics are going to be the same back then as they are now because it's a fractal, and the fractal has a property of self-similarity. The laws of physics do not change. The laws of physics are the same at the new small scale as they were at the old big scale. But if you could look back in time, and we can because light, has a finite speed, we can look back in time and it's going to look redshifted. So that's one way that he explains redshift and the expansion of the universe. And it actually matches the rate of expansion of the universe that we see. So if you look up Blair McDonald, or maybe I'll send you one of his papers. He maps it all out very nicely, and so
well, the thing is, if there's any other reason why light could lose energy, then we have to do the whole calculations all over again, because then you can't just assume it's all space expansion, right? So either way, it's a problem. And even the funny thing is, did you know that even Hubble didn't think it was just space expansion?
Yeah.
Even he doubted it. Yet people just assume, oh no, it's all space expansion.
Yeah.
I think it's kind of naive, and
it is very naive, and you're going to misdiagnose the universe if you do that.
Yeah, right? And the age, and now they're finding all these old galaxies. Like initially, I remember this picture where you have the sort of the zero, like the beginning of Big Bang, and then there's this time like 1 billion years where there's nothing, right? The first stars form after 1 billion years, but now they find complete galaxies after like 300 million years after the Big Bang. And if you read, I read some of these papers, some of them contain oxygen. Like oxygen is something that takes, it's quite it takes a long time to build, to form. So it gets harder and harder to explain.
Yeah, exactly.
Do you know how long it takes to rotate the Milky Way around one time? What do you think? How many years does it take?
I think it's only spun once or twice in the whole billions of years that the universe.
Well, it's about 200 million. It's about 200 million years for one round. So if you're saying a whole galaxy can form within 300 million years, that's like 1.5 rotations. It doesn't add up. Okay, there's no way we can get a whole Milky Way, because when you look at the simulations, it takes many rounds for rotations to get this whole structure built. The time doesn't add up. So, my guess is that we'll find older and older galaxies and realize maybe something's wrong with the redshift. Maybe,
maybe something's wrong with the Big Bang Theory, right?
I think so, because see, it's funny because I used to be a fierce defender of the Big Bang. Like, oh, we know everything, like millisecond after. And then later I ask these questions and I'm like, more and more questions. Like, oh my God, this doesn't add up. That was hard for me, actually. Like, oh no, I believed in this and now it's wrong. Probably. I don't know for sure, but
well, it can be wrong. It might be wrong. We always have to be asking the question: are we wrong?
I might be wrong, of course. But the thing is, there are other discrepancies. Like for instance, how they for supernovas they say, well, they're time dilated. The farther away, the longer I think the explosion is. But then it doesn't. But not gamma ray bursts. So gamma ray bursts don't have the time dilation. So, I mean, either you have time dilation as you go back, or you don't. You're not going to have it. Oh, we only have it for supernovas, but not for gamma ray bursts. Like, what's what the explanation is, the official one? Do you know what it is?
Unless gamma ray bursts are close by.
But they're saying it still works, because it just happens that gamma ray bursts back then behaved differently to just cancel. Coincidentally cancel the effect. It's like, come on, this is too much coincidence.
So they have to make stuff up to accommodate for new.
This effect that earlier it was anyway. And then there's Tolman surface. There's so many things that just don't add up. I wish people would be more critical and ask questions. Nobody's saying it's wrong. It's just you can't even ask the question. Like,
Yeah.
people get aggressive when you just ask, how can you be certain? Should we maybe look at other models too, you know?
Okay, that's what I always say. So there's what, 7.5 going on 8 billion people on this planet. Why can't some of us just look at a different way, but be taken seriously? Right?
Yeah, I'm fine to be wrong. I know I make mistakes every day, you know, but just ask the question and find evidence, and, you know, if it matches better some other model, why not consider it? You know, that's all, you know.
My fractal paradigm, the fractal paradigm does explain why there could be what looks like fully formed galaxies earlier in the universe, right? Okay. Because when I zoom through the Mandelbrot set, you know, here's one region on the left here that I found that looks awful lot like this galaxy here.
Okay.
Like if you look at it structurally, you see the spiral arms, you see like this on the left here, you got this sort of galaxy thing. And on the left here, you have this sort of formation here. Of course, this is much more, the fractal, the Mandelbrot fractal is much more contrived than the actual galaxy, but the morphologies are very similar. Okay. So
yeah,
you can't say the universe isn't fractal, because here's the thing I generated with the Mandelbrot set that looks an awful lot, that has the morphology very similar, spiral arms and structure as this fake galaxy here.
Okay.
And so you can't say the universe isn't fractal. Now, there are a lot of people out there that are trying to prove that the universe isn't fractal, and using kind of hokey math to make this sort of bold statement that they're trying to prove that the universe isn't fractal. And I'm trying to prove that the universe is fractal, right? So here, this is from my paper, the Mandelbrot set as a quasi-black hole, which is I call this my masterpiece, because I think I wrote it really well and it's kind of fun.
Pre-GPT, right? Pre-GPT.
Yeah. No, this was way before ChatGPT.
Just kidding. Yeah.
Way better. But I wrote this for a conference that was, it's called Bridges, and it was supposed to be an art meets science.
Okay.
Okay, so I wrote this. I wrote, my first iteration of this. I sent it to them. I thought they're gonna love it, because it's art meets science, blah, blah, blah. And it was peer reviewed. They peer reviewed it. So they sent it to a black hole specialist, and he rejected it fiercely. He rejected it. He wrote his rejection, his criticism of the paper was so harsh, it made me cry.
Oh.
I cried, because first of all, like, this is an art meets science. Like, I didn't think they would take it like so seriously.
Yeah, right. Yeah.
So it really broke my heart. And so, but then I rewrote it. So I took their criticism after I picked myself off the floor. I rewrote, I took the criticism. Okay, so they were criticizing me because I didn't stroke the ego of relativity. Okay. They're mad at me because I didn't write a chapter on relativity. And this was just like, I didn't want the paper to be too long. I didn't want to waste time talking about relativity.
Of course, yeah. I mean,
pretend that if relativity didn't exist, could we still intuit the existence of black holes? Could we still guess that there's such thing as a black hole? The Mandelbrot set is very much like a black hole. Okay, it's got this central region where the points converge, they never escape. So you've got the event horizon, you have a black hole, you have an event horizon, and you have a photon sphere. Now, people don't realize that black holes also, there's a concept of a photon sphere, and this is where photons travel in strange.
They go in circles, right? Oh, they're just stuck there, kind of.
They call them orbits. So orbits don't have to be circles.
Yeah, of course.
In their mind, they're probably circles. In my mind, so in the Mandelbrot set, the points in the middle travel in orbits but converge, and the points in this region, the outer gradient region, travels in circles or in orbits, but then they escape. But there's a similar thing with normal black holes where in this photon, they call it a photon sphere. Most people don't know about the photon sphere. Only by writing this paper did I discover, there's such thing as a photon sphere that matches what goes on in here, where the photons travel in orbits, but then they have to escape. They do escape. So in the photon sphere, photons, not only can they escape, but they have to escape. And the points in the black hole never escape because they converge to a singularity. Same thing happens with the Mandelbrot set. The points converge, okay, and they diverge on the outside. And at the event horizon, this is where all the sweet stuff happens, right? This is where all this stuff happens, is at the, what I call the event horizon of the Mandelbrot set. So no, it doesn't look like a sphere. It's not spherical geometry like the normal black hole, the Schwarzschild black hole. But this is behaving like. So I thought,
interesting, the connection. Yeah.
I thought they would find it. Oh, and then when you get at the event horizon, the trajectories are so, they take so long that you end up with pictures like this. So here, this is in my paper. Okay, so the images on the top are known objects in space, and the images on the bottom I generated using the Mandelbrot set.
Oh,
so
really?
What I did was I randomly selected points because I didn't know where they would be. I didn't even know what they would be. So I randomly picked points that had high iteration. So the closer you get to the event horizon, the more iterations it takes, right? Yeah. To before it escapes.
Oh, yeah.
So I'm only looking at the ones that escape here, right? And so I looked for, like, 100,000, 200,000 iteration, million iterations, whatever, big high iterations, one just randomly. And I wrote a program to do that. And then I just said, okay, I'm going to let it find it and then take a picture. And, I went to bed, woke up, and there were, hundreds of images that I'm like, oh my God, these are cosmological images. So I colored them to match, the colors are arbitrary.
Of course. Yeah, obviously. Yeah.
But you can see the morphologies are very interesting. Like the morphology of the Stingray Nebula is very strange. It's got this weird, shape. And I found tons of them that look like the one on the bottom here, that strange shape. Right, here's another one that's got that sort of shape, and here I found one like that. So I thought this was really interesting.
Cool. So, wow, interesting.
So there's cosmology built into the Mandelbrot set. I always thought there was, but then when I found this, I'm like, so this is one way of finding cosmology in the Mandelbrot set, and this is another way of finding cosmological objects. So no, you can't tell me that the universe isn't a fractal. And not only that, but it may in fact be associated with the Mandelbrot set, with this fractal, right? Oh, sorry.
Maybe.
Right? It's possible. It's plausible.
It's funny. I used to have a ring with the Mandelbrot on it because I thought it was so cool. I wrote, of course, I implemented. It's the first time I could program. That's what I implemented, Mandelbrot.
Yeah.
So I know. Fascinating.
Like back in the day, I don't know, I think I had my Commodore 64. Well, it was okay. So in 1985, I think that was the first time the Mandelbrot set was popularized because a friend of mine actually, he was a professor at my university, Key Dutney, wrote an article he was writing for Scientific American. So he wrote the mathematical recreations, computer recreation section for Scientific America. And so he was the first one to popularize the Mandelbrot set because he wrote an article for Scientific American and wrote the pseudocode. He wrote the algorithm in there. And then after that, everyone was doing the Mandelbrot set. So I have to give my friend Key Dutney, who passed away a couple of years in his advanced age, but he's the one that did all that. So I think he started the fractal revolution and all that stuff. I would probably put it in the hands of people like me and you and my brother. So yeah, so that's so my main goal is to find that fractal, if the universe is fractal, why, right?
Oh, that will be an interesting question. Yeah, that will be hard to answer. Probably.
And it's not going to be provable, but
probably not.
All I'll be able to do is say that the universe can be a fractal. You can't prove that it's not a fractal. I tried it. The tests that they do to prove that the universe isn't fractal are inherently flawed, and so I use the same tools that they use to prove that the universe isn't fractal on a fractal.
That's funny. Okay.
And
he proved that fractals are not fractals, basically.
Right? And I got the same results as they did.
Yeah. Okay. Well, that's a good idea.
So
That's
their
clever.
tools are flawed. They're misinterpreting. I think they're misunderstanding what it means to be a fractal. They're thinking of clumping, and so what they do is they have this test called circles or points in spheres. And so they look at a small region, then they look at the bigger region, and then they look at the bigger region. They say, well, at some point it looks homogeneous. Well, same thing happens. Like if you look at a fractal and then you go further and further and further away, it just looks like a blur, right? So they're misunderstanding.
Oh, I see what you mean. Yeah.
So that test doesn't work. So yeah. So I don't, yeah. And the same with the ether. We can't prove that there is an ether. We can only prove that there can be an ether if we want there to be one.
And also that, science doesn't really make sense if we don't have one. I mean, yeah, sure, you can always come up with some explanation, but it just won't make sense, right?
Yeah.
If you want it to make sense, you add the ether. Everything's so simple. I mean, Einstein even said, I don't know the exact quote, but it should be simple as possible, basically, and you shouldn't need all these extra things to explain something, right?
Yeah.
I mean, yeah.
I agree 100%. There can be an ether, and when there is, it makes it much simpler. So that's the Occam's razor. The simpler solution is the better solution.
Because, that's how I kind of started, when I looked at these different interpretations of quantum mechanics. I have a slide on that. You want me to show that one? Because if you should we go back to the spin thing, because we kind of went off topic. So
sorry, I kind of hijacked this whole thing. So I want you to talk about what you want to talk about. So share your screen.
Okay, yeah. Let's see.
I will put it up.
Share. Where's the share button?
So you go settings.
Oh, down there. Oh, present. Okay.
And then
share screen. I'll try to share my big screen this time.
Yeah.
Let's see if that works. Is this that one? Yeah.
And then you have to click the window that you're there we go.
Are you seeing my screen now? Okay.
Yeah. So no, I don't. Yeah, there you go. Perfect.
Just a brief. I mean, just that one slide, because see, that's kind of what got me thinking, among other things, is quantum physics has all these weird interpretations. I mean, one is weirder than the other, really, right? Like the Copenhagen one, right? That everything is just a probability.
Yeah.
But then how do these probabilities interact with each other? There must be something real behind it. Otherwise, it just makes no sense. Okay. Yeah. The many worlds to me is crazy. Like, basically, right, at every decision point, there's a new universe. Well, how do you get all the energy from creating all these? It makes no sense to me. Yeah. Then there's all the other ones. And this one is sort of, at least has some real element to it, like the pilot wave. The thing is, you have a real wave.
I like the pilot wave. I like the pilot.
The thing is, you have the wave, but you have the particle on top of it.
Yeah.
That's like, why? You can just have the wave. You don't need, why do you need both? Like, you have the wave plus the particle. What's the particle? So you have the problem with so this is why I think there's not even a name for it, like the neoclassical model, where what about it? Maybe it's just a wave. That's it. You don't need all this extra stuff, all this weird explanation, right?
Yeah.
And don't worry, I'm not going to go through all this.
No, it's fine.
No. But of course, if you have this theory, you have to be able to explain everything.
Yeah.
People will complain right away. Hey, what about general relativity? What about special relativity? What about this and that? You need an explanation of everything. So, and luckily, a lot of people have done this work, like Robert Close and John Mack, and a lot of people have worked on this. And so things that are clear are like, Schrödinger can be derived from this, general relativity, special relativity. And we can talk about this maybe another time, right? To deep dive into this. And of course, for me, the question was what spin 1/2 has to be explained as well. If we can't explain spin 1/2, then we're in trouble. Then we can just throw it away, right? Because electron, everything has spin 1/2. So that's basically how we get back to that simulation. And so my goal was to be able to find a way to simulate spin 1/2. Right. And so last time when we talked, right, we had this Unity implementation, which is kind of complicated. And so you had the great idea to say, hey, you know what, maybe let's try something else with JavaScript. And I'm like, okay, fine, with the help of GPT.
That was
maybe it wouldn't be such a pain, right?
I'm so happy you did that. I'm so happy. You saved
the new
work.
model. It took a few iterations, but it was really funny how it said, "Oh, I'm thinking. Oh, I'm enjoying this." It was so funny. Like, wow, okay, cool. And then it makes mistakes, but finally got it working, and now it's much easier, right? So I think you have to. We can add the link to the description. That this is Java JS Fiddle, and you also have the implementation. Maybe we can go through yours as well. So we have now re-implementation of the same thing, so hopefully people can understand it, right?
It really opens it up. It really opens it up. So people that use your platform can look at it there. And I like the P5JS because I feel like, well, I mean, it's 6 of one, half dozen of another, right? So people could use what you're using there, the JFiddle, and people can use P5JS.
Yeah, and then exactly.
P5JS has a lot of physics built into it.
Oh, I see. Okay.
So that's why, and I'm familiar with it. So I like things that I'm familiar with, but it's mostly because it has the physics. And so now I'm looking into how to implement these spring masses to actually implement the medium for real.
That'll be cool. Yeah, I'd love to see that. Yeah.
So these are just animations that show what the simulation should do, right?
Yeah, exactly. Yeah, that would be really, really cool. So there are a few challenges, though. I mean, it looks easy now, but it's easy to also mess it up. The thing is, it's not just initially. I remember when you asked, well, like the wave is going around after 360 degrees. So where's that 720 degree thing?
Yeah, I had a hard time with that.
Yeah, right. It's hard because the wave is going around after 360 degrees. The thing is, though, the thing in the middle, though, that's the key, right? If you so this sphere, right, it's just added on as a visual aid.
Yeah.
There's no sphere. There's no particle.
What you're doing, I think what you're doing there is you're taking the particle in the middle and enlarging it really big to show what the dynamics is, basically.
Yeah, we can also just highlight this red point here. So I just marked one red dot, like a grid point, to see what is this dot doing. And when it's kind of hard to, you have to watch it a few times, but when you like it's going around. So let's starting here, right? It's going around once, and then it's going a second time. It takes 2 rounds for this big wave to go around. So this. And if you picture this inner thing of being like an electron or a proton or something, like that wave, you can see it's actually spinning, even though there's nothing really spinning. It's just.
It looks like it's spinning. It does look like it's spinning.
Yeah. And exactly. And that's the same thing as the wine dance and the cup trick with the belt attached. So
I do that a lot now. I people will see me, what are you doing? Oh, I'm doing the belt trick.
Right. Yeah. Yeah. So, and do you want me to go through the code briefly to show like what the key elements are? How do you make this work? Why is it working? What do you need for that?
I don't like the code. I think is going to be hard to see for people to see, but
let's see. I can enlarge it. Let me see.
Okay. Yeah.
Can you see it?
Yeah.
So there's really only 2 methods that are important. One of them is the animate. So that one is every frame, it recalculates what everything looks like, right?
Yeah.
So at every frame, we have to transform this whole stuff. That's basically it. And for this belt trick to work, we need a time-based function. So we have this quaternion that's basically the y-axis. That's time-based. So as a function of time, it rotates this way.
Yep.
And then we also have this. I don't know, I call it winding of space. Actually, this is Mark Snowswell, right? He actually made it. He explained it to me so that I understand it. So he was actually the one. Without him, I couldn't have.
I looked at this stuff. I like he's building a kind of a language around it. I like that.
Yeah, exactly. So the winding, this is if you look at the axis sticking out of the window, then that's the space-based quaternion. And basically what we're doing here, right? We have the maximum rotation in the center, and then it just tapers off, right? That's it. So basically this power thing, it just says how quickly does it taper off. So if
actually
localized,
the power thing kind of determines the extent of the wave. So I wrote a slider bar into mine to modify that power, so I can turn it down. When you twist a lot, then it kind of goes off the medium. Right, it goes affects the whole medium. The more you twist it, the more of the medium it affects. So I wrote a variable for the power to pull it back so that it stays in the middle. So it stays in the middle.
Okay. So in Java, I'm using this library called 3.js. So I didn't have to write it myself. And really, there's only really these two parts. It's a time-based quaternion, which is just, here you basically specify which axis. So that's the y-axis. And you specify the phase. That's the time-based. And so what I can do, we can easily change the axis if you want. You can flip it around and it will look like a rolling motions, right? It doesn't have to be the y-axis, but it has to be a different one than the space-based.
Exactly. So one axis is the time, and the other axis is the twist.
Yes. And then we need
whether it's X or Y or Z, it's arbitrary. Yeah.
Yeah. The inverse is just, so if the time quaternion is this way, the inverse is just going the other way. So if we didn't have this kernel thing in the middle, it would just be this way and that way, nothing would happen. So, that's basically when you put this 1 into 0, it still does the motion, but you won't see anything because it goes this way and that way. And it just cancels each other out. So the only thing then...
No, go ahead. Yeah.
So then all we do at each animation step, we have to transform each object. And it's really important to transform the original position. So initially, we create this flat grid, I add a sphere, this belt. We have to remember their original locations. That's one thing I messed up initially.
Yeah.
So then what we do is for each grid point, for the sphere, all these are transformed the same way. So let's just take a look at transform
each
function.
point transforms the same way.
Yeah, exactly. It's just that one function transform, whether it's a marker point or whether it's a grid point or the sphere, it's the same function. Okay.
Yeah.
So now all we need to do now is based on whichever point we look at, we just calculate the distance to the center. That's the radius. And now my mouse went away. Where's my mouse?
It's on the other screen. Maybe. I always lose my mouse when I do double screen.
No, I think sometimes with Teams also when I share. Oh, no, it's back. Look, when I share my screen, I don't know if this is something related to sharing. So anyway, here is we just calculate the radius, and then this is just how the function tapers off, and then all we have to do now is multiply. So we take the time-based quaternion, we multiply with the kernel, and then the inverse, right? So why does this work? Far away, right?
The conjugate, right? You call it.
Yeah, exactly. Because far away, that k of r, that kernel function of the radius, when the radius is large, there's nothing. So it's the identity. So then you have this times the inverse is the identity. So nothing happens. So that's why it works. And the cool thing about this, you can actually construct different functions. That's not the only solution.
Yeah, I saw that on
this inner function. You could even how do you call this? You can replace this whole thing with a whole other function like this inside. So you can have spin within spin within spin.
Yeah.
Also it can be. So this is just a very simple function here, but you can also have a ring-based. So now
that's so cool. That is really cool. Yeah.
Well, it's the ring. Of course, it would be
so what is
a sphere? Of course, this is only. I'm showing a flat plane only, right? But we can have the center still, but only have the sphere going like this. Yeah. And I think there are also probably torus-shaped solutions. I have to, think about that before.
Between the ring, so a ring is a torus, though, no? Or what is the ring?
Yeah, I mean, actually, right now we have two axes. We have the time-based axis, the vertical axis, and the space-based is still the same. It's still the same axis. What if we actually instead the axis is a circle? So, yeah, you know what I mean. It's kind of hard. I have it in my head, but I need to program it. So because I think
I see that maybe in a fractal paradigm too, because you said you can have a current, a wave within a wave within a wave within a wave. Now I'm going to play around.
Definitely
play around with that and see, see what happens.
Yeah. So Mark Snowswell, he has this nice way of calling it the bracket notation. So
I like that.
So this left arrow is the time-based quaternion. That's the inverse, and then in the middle you can have the kernel, whatever that is, and you can see here also. It's just you can use it as a matrix. You can view it as a quaternion, right? Then you have the kernel function. Again, you can view it as a matrix. It's very very simple, really. And then and then so the other thing is, this is what I meant, and it's not the correct visualization. Okay, it will look a little bit different, but I think I should be able to construct this at some point. Yeah, because the thing is, I don't think we know really what is the spinor function of an electron or proton. I don't know. Are they the same, or I mean, are they nested? I don't know. I haven't seen any papers on this. I don't know if you have seen anything about this at all, because I'm not sure anyone knows really.
No, I think we're making it up as we go along, really.
So and could we do experiments?
Experiment with it
to show this. So yeah.
Because what is the difference between the wave function for the electron and the wave function for the proton? Protons also spin 1/2, but is it the same spin 1/2 as the electron, or can you have more spin 1/2? Right?
I don't know.
The proton is quite a bit smaller. Now that could just be because the frequency is high, the Compton frequency. So in my model,
exactly, it could just be a lot smaller, right? Yeah.
Compton frequency for the electron is the Compton wavelength for the electron is bigger than the Compton wavelength for the proton. So the Compton frequency for the electron is slower than the Compton frequency for the proton. So as the Compton frequency gets higher, the space that it occupies gets smaller. Right. And for my
exactly.
Space is at the Planck scale, and so that gives sort of a nice sort of fractal paradigm. But are these, can you add? So maybe atoms are just wave functions on wave functions on wave functions.
It's possible.
So that's really an interesting thing that we can experiment with.
And I think my mouse went away. Oh, now it's back. Okay. So another thing what I did here, I added these markers. So I just picked random points in that elastic solid, right? And you can see that it's doing these circular movements. Of course, they have a twist too. You can't see that, right? It's not just going in a circle. It is doing the same movement, but you can see that on top they're all drawing circles in one way, and at the bottom they're going in the other way. And we're getting back to this magnetism again, right? Because now you have this direction, and you have this north and south. This is one direction, and then at the bottom it's the other direction, and so on.
So I started drawing those objects as squares instead of spheres, and then you can actually see the precession. If you draw them
I see what you mean.
Instead of spheres, then you can see it's obviously precessing, but it's hard to see with the sphere. You can't see that. You can't see it reorienting because the sphere orients the same, looks the same no matter what orientation it is. So if you change those two boxes, use the box function.
Oh, nice. Yeah.
And I think it's the same function as just box instead of sphere. Then so I was able to see the precession better when I did that, because at first I couldn't see it. And then you gave me that nice where you put the cone in, where you put the cone on the side.
Well, I couldn't figure out how to orient it.
No, but I still use that. I use that in my video on the And when I do show people the belt trick, I kept that in, because you can see when you're twisting, you can see the cone gets reoriented.
Oh yeah, that helps.
That helps you see that when you're twisting, you're reorienting everything. And so when you go 90, you don't see, but when you go like 45, you can really see the precession with the cone. So it really helped with the seeing that 720 degrees brings you back to the same state, not 320 degrees. So I had a hard time with that, as you know. You helped me out. That actually, one little thing that you did helped me see it. I couldn't see it before.
It is hard, and many people have trouble seeing it. It's because people just see the big wave, and and also
they see 360. Like I was like, oh, it's still 360. I go 360, and I'm back to the same state. You're not seeing the precession. So. Yeah,
exactly. And one thing I want to mention also, ChatGPT is so helpful. Like today, I just pasted the whole code in ChatGPT. I asked it, although I like your layers, you have these layers. I'm like, can you just please add me some layers? Sure, blah, blah, blah. Copy paste. There's one mistake or something, but now I also have the layers. It's
nice.
It doesn't look as great with gray, but but it's ChatGPT is so helpful to make them. You still have to check your code, of course.
Yeah, no, that's neat. I like that. So, I have my style for visualization, and you saw the video that I made, and I have I want to try to do a medium. So I want to try a medium, and I want there to be, the spheres are particles, or they could be squares. I could put square. When you put the squares in, you really see the the precession of
exactly.
Point in space is going through the precession, right? But the spheres look prettier, so I'm always torn between, should I do the squares or the spheres? The spheres look more like what the BEC looked like when in John, when they form these solitons, these vortices in the BEC. They're not squares, they're circles. So I want to try to implement, and I believe that the medium for the propagation of light is like that. So where there's spheres, probably spherical regions of space, or it might be a continuum. And that I
don't know. I have no idea. So I'll right? I don't even know if it's crystal. I mean, I know crystal works mathematically. So Hagen Kleinert, he has started this whole thing. It's got to be elastic. So the only question, if it's a fluid, I haven't thought much about the fluid, but if it's a fluid, it needs to keep its shape, right?
Yeah.
It can't just be flowing around, because then it will destroy the waves. So it's got to be at least very kind of rigid, right? Otherwise,
rigid. Well, in the BEC, those solitons that form in the BEC are kind of pinned in place. So it's not a solid, like there's an attraction between the two, but because there's a repulsion, there seems to be some sort of repulsion that keeps them separated. And actually the same thing happens with the ferrofluid, which made me think that the medium for the propagation of light is like a ferrofluid, like it's a colloid solution that, far away from any matter, that these, the medium molecules, particles, whatever, solitons, I think soliton's a better word. So the solitons repel each other and they form this hexagonal pattern. And that's why I'm using the hexagonal pattern, because I think once I do start to implement this as a medium with spring masses, that I'm not going to use a cubic construction. I'm going to use a hexagonal, probably, because it makes more sense to me that it would be, if my analogy is correct, and it's like a BEC, where when you try to spin up a BEC, it resists changes to its angular momentum. So it dumps all its angular momentum into tiny vortices, which then repel each other because they're spinning the same way. Like if you have magnets that are oriented the same way, they're going to repel, north and north and south. So they're oriented in the same way or in a similar way, and they repel, and then they create this hexagonal pattern. So that's why I'm using the hexagonal pattern. So eventually, and so it doesn't have to be a solid, it doesn't have to be a liquid, it doesn't have to be a, superfluid, but it might be a BEC, because the BEC has the it has the appearance of a solid, right, where you have vortices pinned in place in a certain place, and out, far away from any matter, it is going to just sit there in this pattern, and it's going to be solid like. It's going to be solid like. And then the only thing these vortices can do is reorient themselves, which we're doing in our animation, and they can get displaced. But when so when a particle comes in and you have some sort of, you're creating, the particle itself is a wave made up of these mini solitons, but the particle itself can move around. As soon as the particle moves away, as soon as the wave particle moves away, the solitons in that region just go back to their normal,
Oh, I see. Yeah, because you would have to explain how this bigger wave could move through really quickly, also, right? Almost,
But when the particle is made of a soliton, so the particle itself is these solitons in motion. Okay, then the wave can move, like the wave can move. Right, we can move the wave with the soliton. The big soliton is made of small solitons, and small, right? And so can move away, and then the small solitons, the medium for the propagation, it just goes back to the way it was before. So you're not actually moving through the medium; you are the medium.
Yeah, exactly. That's important. So the wave is just like a water or a sound wave or earthquake wave, because that's also solid. Well, the Earth's not exactly solid, but you have these longitudinal. Oh, well, that's the other thing, right? I mean, in an elastic solid, you have transverse and longitudinal waves.
Yeah.
Now, I'm not sure we have detected longitudinal waves yet. So, I mean, if there are longitudinal waves, I don't know.
Yeah, I think gravitational waves are longitudinal waves?
Maybe. Well, that's possible,
Because
right? That kind of makes sense.
Yeah, I have
So,
a paper I wrote. I talk about this. I have a paper I wrote called "The Medium for the Propagation of Light Revisited," and I do talk about the possibility that that gravitational waves are longitudinal waves, and that when black holes collide, it creates an earthquake.
Yeah, exactly. Earthquake, like pudding shaking, right?
You get the transverse wave, and you get the longitudinal wave. Okay, they detected a longitudinal, the very first detection. They say it's a transverse wave because there is a little bit of up and down motion, and in earthquakes, of course, there is the longitudinal wave is detected before the transverse wave.
Well, yeah, that's the interesting thing. Right? Faster normally.
It's more subtle.
A little bit faster. Yeah.
It's more subtle. And so when you look at the longitudinal waves, there's still a little bit of up, and that's how they detect it. There's a tiny up, and they have to really zoom in on it to see this up and down motion. That's how they detect it. It's a smaller up and down motion, but it is a longitudinal wave. It is a, but it squishes the Earth a little bit.
I see what you mean. Right. That would be interesting. But how could we detect it, right? So that's the question.
So but the very first time they detected a gravitational wave, about 0.4 seconds later, they detected a gamma ray burst. So, right? And longitudinal waves in earthquakes travel a little bit faster.
Yeah, they're a little bit faster.
They arrive first, and that's how you can kind of guess that there's going to be an earthquake. And the animals always know which way to run when there's an earthquake. So the animals, when there's that earthquake in Indonesia, no animals got hurt because they're touching the ground. They can actually feel this longitudinal wave, I believe. It would, even birds could feel it, because if they're sitting in a tree, they're going to feel the wave. It's going to affect the whole bulk of the medium, just a little bit subtle.
Yeah.
And so they instinctively know to run in the direction of the wave, the longitudinal wave. The longitudinal wave arrives first, and then the transverse wave is the one that does all the damage, because it's
that would be a good question to ask about the universe, because people are so stuck on C's. Of course, C's constant in the medium. I'm not questioning it at all. Okay, but if the medium is a substance, then it could be that the longitudinal waves don't have exactly C. It's possible, and people should actually really investigate that, not just assume, oh, it's got to be C. I mean, not going to even question that, right? No, probably it could be C, but what if not? I mean,
we can't know, but. So the transverse wave, so in the gravitational detection that they had, they saw, they detected the gravitational wave, which I believe, and then 0.4 seconds later, they got this gamma ray burst. So now I saw a paper on this. I wouldn't know about this if someone didn't write a paper on it. So the longitudinal wave arrives first, then the transverse wave. So I think that they are seeing gamma ray bursts coincident. So now all gravitational waves, if they all arrive and then you see a gamma ray burst shortly after,
then that would be a good clue. Do you have to? Can you send me the link to that paper? That would be interesting to read. Yeah,
I will. If I forget, then just remind me. I'll have to dig through my archives to find it. I know I have it because I always save papers that are interesting, but I could probably find it again as well.
Yeah, we could do this AI podcast. I don't know. There's this notebook LM that lets you create these podcasts from papers, which I think is really cool, to help explain things in a simple way and get a summary.
So Notebook LM, I just want to say that, because if I put this up on my YouTube, I want people to know that they can download Notebook LM if you want to make a podcast of a paper. So this is like a wonderful way of hearing a paper without having the
it skips all through the math, but it's able to really it's AI, right? It can really summarize well. You have this almost like a discussion between two people, and of course it makes mistakes. Like they switch roles suddenly. Like one is the expert, one is the one that asks. Suddenly they switch roles, and like what happened? But you still I have to read a lot of papers at work too, so I like to listen to them, like in the garden. Like, I could now, and then I can read it afterwards,
so I highly recommend people that if anyone's listening to this, that you try that. It is very, very cool.
I have like 15 of those already. Like all the papers, I just put it there first, and then I listen to them.
So I'll send you my paper that I wrote, Medium for the Propagation of Light. Probably the paper I just told you about is referenced in that paper, so I'll just have to find it. So there can be an ether, in my opinion. There can be. We're never going to know whether there is or not, but I think there can be. And then if we can show that if we can recreate something that acts like an ether with a simulation of some sort, I don't know, like if we need computers or anything to do that, but I'm going to try and do it on a small scale with spring mass systems.
Yeah, because if you can derive everything from first principles and everything is emergent, you know, like special relativity is emergent, gravity is emergent, then, you know, it's kind of, it makes things much simpler. Plus, there's some things you can't really explain without a medium at all, you know. Yeah, all this weird stuff. So special relativity is another topic we wanted to talk about. Do you want to tackle this now, or do you want to?
No, I think we should save that for, like, we'll focus on that in another.
Because that's gonna go deep, and we have, you know, so basically.
I want to go through. You sent me a document, and I haven't had time to go through that yet because I've been trying to get a couple of videos.
Okay, yeah. It's really actually so easy with the medium. It's almost trivial. Like my kids are like, it's easy. What's the big deal, you know? So I'm like,
how many kids do you have?
2.
Okay.
So I also the electron thing, the spin, like, hey mom, what's the big deal? They came.
I get it.
You know, people think funny. So at least they grow up more skeptical and ask questions. They can question me anytime too. So it's good. But, you know, I hear a lot, like,
that's good though, and that's a good way to try and see if you know it. If you can teach them, then it's a good sign that you know what's going on as well, right? So, like Einstein said, if you can't explain it to a 6-year-old,
I know exactly. That's so.
Well, that's why I have my YouTube channel, actually, because people ask me questions all the time, and I have to really dig deep sometimes to answer these questions. I have to ask myself, do I understand this concept, right?
Exactly.
So that's really helped me clear a lot of things up and figure out how to word things in a way that people can understand.
I know. Oh, I plan. Yeah, exactly. Once I retire, I plan that I want to spend my time doing this, explaining stuff. But I wish I had more time.
How close are you to retirement?
Oh, well, 13 years. I don't know exactly. Depends. They changed the year.
I'm only about 2 years away from retiring.
So. Okay. Well, then you have full time.
If I retire.
Then you have the time to do this, right? So.
Yeah. All my spare time is spent doing this. So
that's cool. That's good.
At least,
There's a purpose. There's a purpose.
Defending my husband without, deserting him.
Good point.
Spend a lot of time
he's sitting right there.
Yeah, I do spend a lot of time studying and researching and writing code to to either validate or not what I'm.
Yeah, because I love writing code, because then when I can write the code, I know I understand it,
Exactly. And that's why I needed to get the code for this. Thank you again.
Totally. Oh, no, that's great.
Well, I'm going to thank you every time I see you, probably, but it's like, I probably could have done it myself eventually, but there were certain things, like I needed to know about this kernel function. I needed to know, because I never really thought to take a transformation and put it between two quaternions before. That was kind of a breakthrough.
That's really the key. I think
that's an important. You can't do it any other way, right? So so hopefully that sort of opened a few doors to some ideas for me. So that's really cool.
You want to go through your code too and see how you did it in your or
I'm gonna do, actually, I've been reworking my code for my audience. My audience. I have an audience.
Wow. Yeah.
And so I get it. I grok it. 100% get it.
Okay.
And so I've just been like rewriting the code to be to document it. So like I already gave out the code last night. So I'm hoping people kind of look at it. And then, great. So I 100% get it. It's exactly the same as what you did, only I'm using the 4x4 matrix version of quaternions. That's really the only difference. And I do that just because I can, and because I think it'll be easier for people to understand that that have a hard time with algebra, with these symbolic. So basically, everything's a 4x4 matrix. The quaternion is a 4x4 matrix. The location is a 4x4 matrix. The everything is a 4x4 matrix, and that way they only have to worry about one thing. I don't talk about vectors. So I've got quaternion, and so I have locations, orientations, and 4x4 matrices.
Okay.
So locations, the locations don't have to be 4x4 matrices, but they can be too. They can be.
Just if you
When you pass in a location like the XYZ, you know how they normally set W to 0 or the A to 0. You can set that W to anything. Doesn't have to be.
Okay.
So some people make a big deal about, pure quaternions where you set W equal to 0. Well, when you're passing a point, when you're transforming a location through the quaternion matrix, that W can be anything you want. It doesn't have to be 0. If you set it to 0, it's fine. You could set it to 1,000,000, it's fine. It doesn't affect the transformation. It doesn't expand anything, or because we're ignoring that. When you're doing that operation, you're ignoring that scalar. Okay. It doesn't come into the equation. And so, but you do need the 4x4 matrix, the transformation matrix, when you're doing the transformation.
Yeah.
The kernel function has to be a 4x4 matrix.
Yes.
In my code. And the other quaternions, the rotation quaternions, the rotation and the complex conjugate have to be 4x4 matrices because it's a transformation matrix. So Hamilton's, those 4 equations that you find in the function, right? You know how you have like the transformation in the function where you do the transformation, there's 4 equations. Right? In the multiply matrix function, there's 4 equations. Right, those 4 equations are matrix multiplication.
Yeah, right.
So you can just as easily do matrix multiplication.
Exactly. Yeah. It works the same. Yeah.
Right. So those equations, like, you know, that might confuse people because then it's algebra, right? And algebra I know confuses people. But if you just say it's a 4x4 matrix and then you're multiplying a point, you just multiply the matrices together and then you pull out the top row to get your answer. Then it's just you're just doing the same thing over and over and over again. It's just matrix upon rate. You can concatenate your matrix, like what the software is doing is it's taking the kernel and then applying the rotation, and you could probably apply another rotation over top of that, and then
so next step will be you have like a text box where you put in a formula, like you have a rotation about X and then about Y and then about Z, and then you can get these really crazy spinners.
Yeah, for sure. So I started to try that yesterday, and I'm like, no, stay focused, because I wanted to make these videos. I always get sidetracked so easily, and so I tried not to get sidetracked. Like, no, I just want to finish these videos. I have one more video where I want to show them, tell them how my code works. Look at the code.
You're going to walk through. Okay, yeah, makes sense.
Walk through, and then then I'll be done with that. But
it's kind of, I get obsessed too. Like it's kind of. It's so you think about it more and more, and it just doesn't let you go for some reason.
I know. So it sounds like we're very similar. We're very similar in that way. I'm not sure, why we're like this, but I'm definitely a little obsessed, OCD about this stuff, and it's fine. It's fine. I feel like I'm onto something really good. And
I feel like we should have some kind of discussion with some people like Robert Close and John and some others to ask these questions, some of these questions, because I know everyone. The funny thing, people kind of focus too much on what they disagree on. I think it's this is different, but instead we should look at all what's common. Like we know there's a medium, we know these are waves. Like there's a lot of common things, and maybe there's some common elements we could get ahead.
Yeah.
What about whatever that topic is? Charge, something else. We don't have to focus too much on the differences. Like Marek will say, it's this kind of crystal, and this guy will say, no, it's a continuous. Like it doesn't matter to me. It doesn't matter because it's still what's important is there is this medium.
In order to simulate it on a computer, I need to have discrete points.
Of course,
whether it's continuum or not, I still need. It's kind of like the universe could be infinite, but my computer has a limit to the digits of precision. I can only zoom into my fractal a certain amount, and then it stops. There's only
shown, and I think Robert Close and Marek probably both have shown that it doesn't matter, because if you zoom out enough, it won't matter. Like you wouldn't be able to computationally even see a difference. Yeah. So whether it's continuous or not, we will never find out probably anyway. Yeah. Like because even at the Planck scale, if there's another level, we wouldn't know, right? So,
we couldn't know, and I probably
we might as well say, maybe it doesn't really matter. Yeah. So we can only say this, what's at least like the minimum size it will have, or not actually the maximum size, right? It's probably at most Planck scale, right?
Yeah. Exactly.
Because if it was larger, then how could we have smaller things in Planck? Well, than this, then so it's got to be.
Or is the Planck scale even real? Because we do derive it kind of just sort of mathematically. We derive the Planck scale. We don't know, but I'm still modeling with the Planck scale.
Okay, good question.
Is that even a real thing? Right? I think it is, because I have a particle at the Planck scale that is self-similar to the proton and the electron in my model. So, and you kind of, if you need a medium to be smaller than the objects it's creating.
Yeah, obviously, yeah, a lot smaller. Otherwise, yeah.
But the only thing I do differently is I use H instead of H bar in all my Planck unit calculations, and I interpret it differently. I interpret it as the Planck length as the circumference of the circle, the wavelength of the particle, which is the circumference of the circle. Same thing, right?
Okay.
The wavelength of the electron is the circumference of the wave model. So they're the same. So
it's just a factor, right? Yeah, it shouldn't really matter. Yeah.
Like you can see, when you take a circle and you animate it, and then you draw the wave, the wavelength is equal to the circumference of the circle. So
this is how you see it.
The Compton wavelength is the circumference of my model.
It's okay, I see. Yeah. Okay.
So those things are, instead of saying, wave is, one thing, and no, they're the same thing. It's just easier to draw as a circumference of a circle.
Okay.
Right? So, and it is if it is a soliton wave, it is a, occupying a spherical area, and then the Compton wavelength is the circumference of that spherical.
Okay, yeah, makes sense. That makes sense.
Because it is a wave and it's spinning, right? So
yeah.
That's why I use H instead of H bar, because H bar is calibrated to the radian, and H is calibrated to the cycle.
Oh, okay, yeah.
H bar, so it's E equals H bar times angular frequency, which is radians per second. So it's calibrated to the radian, and E equals HF. Frequency is calibrated to the cycle, because frequency is cycles per second. So H is that's how I say it. H is calibrated to the cycle, and H bar is calibrated to the radian. And I want to be calibrated to the cycle. I want to be calibrated to the wavelength, and not wavelength divided by 2 pi, because wavelength divided by 2 pi means nothing to me.
Okay, yeah, I get your point. Yeah.
Right, it means nothing.
Yeah.
So circumference divided by 2 pi is the radius. That does mean something, but circumference or wavelength divided by 2 pi, lambda bar, they call it, means nothing to me. There's no, right? It's
right. If you picture it in your head, it makes no sense.
But so I want to do everything in terms of wavelength.
Okay.
So when I use H to calculate the Planck natural units, Planck length is the wavelength of the particle, the wavelength, which happens to be the circumference. So coincidentally happens to be the circumference.
Okay.
So,
yeah, I got a lot more to think about.
My math, ignoring, doing in terms of wavelength and not wavelength. So, so that's just the difference between me and, say, John Mack, and that's what we argue about. Not argue. He has his way, I have my way, and he thinks his way is right, and I think my way is right. It can't be both. It can't be both. That's what I discovered. It sort of, kind of can be both, but it can't be, I don't know. It's hard to explain. Like, a lot of his calculations work out the same as mine. Like, if you take Planck length and divide it by Planck time, you get the speed of light. If you take his Planck length and divide it by his Planck time, you get the speed of light.
Yeah.
Right. So there's a lot of things.
It's
almost 6 of one, half dozen of another, almost, right? So he could do it his way, and I could do it my way, and get 90% of the way there. But at some point, there's going to be a problem.
Oh, okay.
At some point, there's going to be a problem. It's not gonna, he's interpreting his differently than mine, and maybe we're both right. And that because he interprets his Planck length as wave amplitude, and I interpret my Planck length as circumference, as the wavelength of the particle. and maybe we're both. It's possible we're both right.
Oh, okay.
I haven't quite.
Yeah.
I haven't run into a real gotcha, like I'm right and you're wrong kind of thing. I haven't found that yet. So it's possible we're both right as well.
Okay.
So, but I like to just, I really want to simplify things and not have two ways of doing something. I want to use H always.
Okay.
H
Yeah.
always. Always. I don't want to, there's no H bar in my language at all. I don't need it. I don't want it. And I think I can do everything. I can create my medium using H. So one turn of the ohm particle, one turn of an electron is equal to the energy of H, is equal to H.
Okay.
Right? One turn is equal to H, not H bar, but H.
Okay.
Right? So the Compton frequency, so when if this wave has a frequency of the Compton frequency, and then you multiply that by the H and divide that by the speed of light squared, you get the mass of the electron.
Oh, okay.
So, that's how it's working. So H divided by C squared is the mass of one turn, of one rotation of one in our code where you've got the R where it goes around once. Okay, that is equal to, has the energy of H and the mass of H divided by C squared.
Okay.
And when you multiply that by the Compton frequency of the electron, you get the mass of the electron. So it works out really nicely.
Ooh, yeah. Yeah. Right? That's actually really cool, right? Yeah.
Yeah. So it's I think it's self-consistent. It's
that's cool.
model.
Yeah.
Whether it's right or not, I don't know. But when the numbers work out so nicely like that, it's like, okay, so
that's pretty amazing, actually. Yeah.
Yeah. All right.
Well, it looks like we have a lot of more work to do, huh?
Yeah. A lot
of fun, though. A lot of fun to write all these simulations. So, yeah. I'll definitely let you know if I write something else. Not this week, but keep sharing stuff, and then we'll maybe figure some stuff out, right?
Yeah, exactly. Yeah, I like your approach. I like your attitude. I like the fact that you're a female, because the demographic of my YouTube channel is, like I told you, 99% male. Which means that there may be 100 women in my YouTube channel at the most.
So it's that. Yeah, same for me. Like my friends or also at work, it's almost all males because I'm interested in these things that no woman is in. I don't know why, but
yeah. So, anyways, So when we shut the stream down, there's going to be a message that says my part is recording on my side and your part is recording on your side. And what it's going to do is it's going to upload it to somewhere, to the StreamYard. And then I'll be able to download that and then I can send it to you. So you can edit it and put it on your channel. And then if you said something you didn't want to say, you can tell me and I can cut that part out. Then I'll edit it and then put it on my channel.
I think it was okay. I think I tried not to.
Yeah, I think we're good. I think we're good.
Nothing offensive, because sometimes we talk about and then make a negative comment. I don't want to do
I've never done this feature before, so I'm not sure.
Okay, let's try then.
I might tell you not to shut it down until
I'll just leave it running and okay, that's good.
But
it was great talking to you. Let's do this again. Special relativity next time, huh?
We'll do this soon.
Sounds good. Sounds good.
Yeah, next time we'll talk about relativity. More about relativity.
Sounds good.
Okay.
Okay,
right.
cool.
I'm going to end the stream. End the stream.